So this is our plan. We're going to talk about solubility of gases. Pretty simple. Everything you need to know about that, you can think about when you're drinking a beverage. Like if you shake it, what happens to the gas in it? Comes out, right? That's the opposite. That's the opposite of normal. If you add more sugar to water, how do you make it dissolve? You shake it or stir it. The gases and solids are inverses. Interesting. Okay, then we'll go over more diagrams from the AP tests, like representations of solutions, which is what I should have typed, but diagrams was faster. And then we'll talk about chromatography, which was, it's always been on there, but they've added a ton more about it. So like they got rid of math and there's no math in chromatography, but here we go. Ready? The solubility of liquids and solids does not change appreciably with pressure. Okay, so like if I have sugar water and I try and squeeze it, the sugar's not going to come out. It's almost impossible to compress a liquid or a solid. They are in their compressed state basically. But the solubility of a gas in a liquid is directly proportional to its pressure. Okay, now, remember I said everything you need to know about this, you learn drinking a drink. Have you ever had one of your drinks overflow when you open it? Raise your hands. So that's 99% of us. The reason why, think about this, the solubility of the carbon dioxide in your carbonated beverage is directly proportional to the pressure of this that's above it, technically. So here's your pop, and I know, just don't judge my drawing, okay? Okay. Okay, here we go. Here's my pop, and it's just generic brand. You all right with that? And there's, it should be, but I didn't want to select the green marker. There's always air right here when it comes from the manufacturer. And there's a reason why. That air provides pressure. And that pressure is being applied to the liquid. And the gas bubbles are in here, but they're dissolved in the liquid. So we don't really see them or interact with them. Okay. Just like we don't usually see like a sugar molecule dissolved in the water. It's in there. We taste it, but we don't see it. Okay, so the gas is dissolved, but then you like turn it and you hear the sound, and you've been trained by your age now that you know that sound, like the more vigorous it is, the sooner you better reclose that thing, right? Okay, but you're like talking to your friend, or you're at the family reunion and your uncle you've never talked to is right there, and you're wearing your brand new like July 4th shirt from Old Navy. And you're like, and you don't remember that you took this class and that the pop's hot and you're about to remove pressure. And that noise doesn't register. So you just talk, and then all of a sudden, boom, all over your Old Navy t-shirt, right? The Old Navy July 4th t-shirt. Okay, as soon as we remove this pressure, the solubility of the gas, or let me put it in English, the ability of the liquid to hold gas decreases. So gas goes where? It goes out. Easy enough? Okay, so now we know why it fizzes is because there was pressure in here, or why it makes that little psh sound. And now we know why it overflows is because it all comes out quick. Go ahead.
Soluble gases is just like reverse vapor pressure.
Yep, pretty much. We push it down hard and it goes in. Yep. All right, kind of ready for some, you maybe not care, but kind of cool. Drinks that have fizz, we call them carbonated, right? They're carbonated. How come? They have carbon, but also, what is this? Carbonate. Okay. What is this?
Water.
It's carbonic acid. And we've learned before that carbonic acid is not stable. It decomposes into what? H2O and CO2. So when you buy a drink that is, you need a tissue. When you buy a drink that's in a can or a bottle, when it was packaged, they used carbonic acid to make it. Now, if you go to a restaurant and they fill it up, that's coming directly from a CO2 source. And they mix it in the thing.
They have giant cans of
Yeah, that's why they taste slightly different.
But you have to weird those and so many.
Is she talking or mom?
Oh, sorry. Right.
All right. Anyway,
Just myself, not my job.
kind of cool science that applies to those of you that share a love for carbonated beverages like myself. All right, what we've been talking about is Henry's law, which is not mathematically tested. So you don't need the equation. You do need to know Henry's law. Henry's law says the solubility of a gas, well, let me just read it because starting it that way made no sense. Okay, Sg equals Kpg, where Sg is the solubility of the gas, K is Henry's law constant for that gas in that solvent, Pg is the partial pressure of the gas above the liquid. I will. So it's saying the ability of the gas to dissolve, or the solubility of gas, is equal to a constant, which it's a classic chemistry constant where it's different for every single thing and every single temperature, but whatever. It's a constant for those solute-solvent combinations at those temperatures, so we don't really care about it. It's equal to the pressure of the gas above the liquid. Higher pressure, higher solubility, lower pressure, lower solubility. We arrive at that? Okay. Now, you know, if you shake a drink, it goes flat. Now you know if we remove the pressure above it, it goes flat. And the last one, you probably also know, if you let your drink warm up, it goes flat. It goes gross. That's the best way to say it. All right. People often ask me, by the way, this is Tom Davidson, fact number 286.7. They're like, is Mountain Dew your favorite pop? And the answer is no. It is not my favorite drink. Dr. Pepper is my favorite drink, but like medium warm Dr. Pepper to me is terrible. And medium warm Mountain Dew to me is fine. Gross. Gross. You're done. Yeah, well, I typically, if I buy a refill, I'll get it either at 5:30 in the morning when I start driving, or at like 6:45. And so by the time you're here, if I'm drinking a refill, the ice melted a long time ago, and I can handle, like, it's disgusting, but I have an addiction, so I'm fine. I can handle warm Mountain Dew, but something about Dr. Pepper does not float my boat when it's warm.
Like Mountain Dew's like fruit flavor and like fruit's fine.
I think Mountain Dew is called a citrus flavor, and you can almost name anything citrus flavor.
And so it's like it's fine at room temperature
Oh.
because it's
Okay, so it's basically a health food. You can get it at Whole Foods. All right, anyway, moving on. So when Mountain Dew gets warm, I don't mind it with Dr. Pepper or Coke. And it's also weird. Coke and Dr. Pepper dark sodas have they have another acid in it called, anyone know? Phosphoric acid. And for being old and with acid reflux problems, that just kills me. So I really only drink non-dark sodas now because I'm a baby. Moving on, you don't care. This is not AP, this is Tom's life. We got enough of that yesterday. All right. Perfect. Okay, so really that is it on solubility of gases. Just remember it's the opposite of everything we've learned about solids and you'll be fine. Okay, using particulate models for mixtures. So this is drawing again. And we scratched the surface, but now we'll go just a tiny bit more in depth, all right? Particulate models can be used for representing interaction between components of a mixture. So like we got their ion sizes, their orientation of solute ions and solvent particles. Those are the things you may need to draw. All right, and then representing concentration of components. Now, excuse me, like I said, we already did this 2 days ago. We'll just kind of do it again. You okay with that? So here we are. So, and we drew this. This is just better than I drew it. Particulate diagram of salt dissolving in water. You would absolutely need to draw the chloride ion and the sodium ion. You with me? All right, and you would need the pluses attracted to the minus and the minus attracted to the plus. Easy enough. Like that's literally it. It just shows it. So orientation, all right, and then our size. Okay, now here's a weird question. We're going to make a drawing. M plus is an unknown metal cation with the +1 charge. So already tell your friends it has to be one of what's? Alkali metals. So it's lithium, sodium, potassium, rubidium, cesium, or francium. Now, 99.9% sure they would never say Fr because it's radioactive. We don't do it. Okay, here we go. A student dissolves the chloride, meaning the metal chloride, family 1 and chlorine, MCl in enough water to make 100 milliliters of solution. The student then mixes the solution with excess AgNO3 solution, causing AgCl to precipitate. The student collects the precipitate by filtration, dries it, and records the data. Make a drawing that represents the AgNO3 solution before the reaction occurs. That's a lot of words to draw a solution. This would be in a question that had a lot of math also.
Wait, so would we just draw it?
Just draw it. Draw what you think. Or just sit there till we draw it together. Let's see, is it on the next slide? Oh, it is. Good. I don't even have to draw it. Some background knowledge here. You would need to know if AgNO3 is soluble. It's NO3. Good job. So it is. It is. Yeah. Seth, use a stretch.
Yeah.
Seth, have you showed everyone the cake you guys made?
I saw it.
It's pretty amazing.
It's pretty great.
Well, he doesn't have to. You were doing track. Looking good. You got anything, Samantha?
Wait, hold up. What am I drawing again?
You're making a drawing represent the AgNO3 solution before the reaction occurs.
Before it occurs?
Mm-hmm.
Oh, before it becomes AgNO3.
Yep. So we should have MCl in the water, then excess AgNO3. We would have 0 AgCl because that'd be after the reaction. Okay, we ready? All right, here we go. All right, make a drawing that represents the AgNO3 solution before the reaction occurs. Think about the orientation of the ions related to the water molecule dipoles. Okay, so Ag plus would be by the face of Mickey, because that's the negative, right? Yeah, that's how we're going to describe it from now on. And then the NO3 should be attracted to the ears, because those are the H's. Then both Ag plus and NO3 should be larger, significantly larger, and it wouldn't have to be way bigger, but you should draw them both bigger than the water molecules. Is that right with that?
It started at small.
Now, how come I didn't include any MCl? Because it's before the reaction, and this says that represents the AgNO3 solution. It didn't ask for it. Could you?
Yes.
Yeah. So M, if I put M in here, now we couldn't really do the size because it could be tiny lithium or it could be gigantic cesium. But M, we would know at least one thing about it. What would I put next to it? The ears or the face? The face. All right. Because the metal will always be positive, right? It'd be attracted to the negative oxygen and so forth and so on. Good enough? Now, honestly, by the way, if you drew this crappy water molecule, there's a problem with it. What would be wrong with that? I made the bottom hydrogen gigantic, right? Now, not on purpose. I was just being lazy, but don't be super lazy on these pictures. Don't give me any reason to mark you wrong. Okay. Ooh, there's a lot of words. I haven't looked at these in a year. Student mixes dilute AgNO3 with excess NaCl. Ooh, sounds like the same chemistry. Which of the diagrams below best represents the ions that are present in significant concentrations in the solution? AgCl does not readily dissolve in water. Okay, this is from AP, and they have underlined excess, because excess is a very important word in a sentence. So read it to yourself a couple times and then have a discussion with your partner. Which one of these is the correct answer? When you're ready, go ahead and tell your partner. All right, are you ready? So who thinks it's A? All right, good. A is not it. How come? There's what? All right, there has to be excess in there, right? And the excess is the Cl. And yes, Na is too, but Cl is part of the precipitate, right? So it can't be this one. Are we okay with that? Okay, who thinks it's B? Raise your hands. Nobody. Okay, why is it not B? Okay. Okay, there is Ag, and also there's also Cl. So what would these do to each other? If they were still present, they would have bonded and formed a precipitate, right? Okay, who thinks it's C? Raise your hands. Okay, that is the correct answer. So that's good. It made a precipitate. It had excess chlorine. All right, Na and NO3 are spectator ions, and so they have to be there too. But it has no Ag. That's the other major thing. Yes.
If we were drawing this, how would we know, like, how do we know that NO3 is bigger molecule?
Because it's a nitrogen and 3 oxygens, so it would have 14 for 62 electrons to cause bigger clouds. Yeah, it's just the amount of stuff. All right, are we all right with that? What would be wrong with D? There's definitely one thing at least to show you it's wrong. All right, this and this would have bonded, that and that, right? Okay, That's a lot of words, so I'll let you read it to yourselves. Oh, so many words for something that's not very hard, in my opinion. Yeah, so saying put one Li and one Cl. So like a Li plus and a Cl minus. Only use one of those. And then you better draw no more than 5 on each one, right? Because it wants 10. If any AP grader, if you drew 11, if they marked you wrong, like I would be so frustrated. Be like, what? Are we testing their ability to count to 10 or their AP chemistry knowledge? But now we just line up the Mickeys. Oh, that brings back so many bad memories. The Mickey mouse. Anyone know that stupid game? What's that? No? It was like Clausen's favorite game to play with student government kids. No one knows the Mickey mouse. No one knows that game? I can't. It's like talking about Fight Club. You just don't do it. And no one knows what I'm talking about. Anyone know what I'm talking about? One human has culture. Fight Club's a movie and they have a secret Fight Club. But you don't talk about Fight Club. Well, it's a stupid game like you can take a book but not a friend on your vacation. It's one of those stupid things. Don't. All right. It's too complicated. I can't. All right, lithium. What should touch the face or the ears?
Or face, sorry. I drew it right. I swear I drew it right.
Good enough, right? Okay, next. I'm tired of this. So here's what the answer. A clear representation of at least one Li plus and Cl minus separated from each other, labeled and charged. Do we do that? Yep. Each ion surrounded by at least, oh, they want 10 on each. I didn't read it that. Oh no, of at least 2. Sorry, I didn't read. I gotta read. And they need to be oriented with each other. The oxygen end on the water goes closer to the lithium and the hydrogen on the chloride. We all right with this? Okay, don't read that and have a heart attack. That's from a year ago. We ready? Okay. Oh gosh. Hold on. There we go. Will you see if you could answer these 3 questions?
Gosh. Yeah. I didn't know it. Oh, I haven't done the other 2 yet. This is the first one. How did that go? Oh, that's maybe it. That's what we just talked about. Oh,
All right, here we go.
I'm just not very smart.
So number 1, I'm going to start at the bottom. Who thinks it's E? Raise your hands. Good, because it is.
I wrote it down.
All right, that was spoiler alert. An unsaturated solution is one that yada, yada, yada. Oh, tons of bio people fall for number one. If this said an unsaturated fat is one that has no double bonds, that's correct, but that's not this one. What is it then?
C.
It's C, which is a super confusing way to say it, but it's what it is. All right, and then pressure has an appreciable, has not. A lot of the last test, there was one that had the not that wasn't capitalized, and it was a butt kicker. Pressure has an appreciable effect on the solubility of blank in liquids. E. All right, there's your review. Oh, we're supposed to test tomorrow, huh?
Oh, we are?
I forgot about that. Oh, how could I have forgotten?
Okay.
On all this fascinating information we've covered in depth. Oh, my Lanta.
Oh,
Okay, temperature. This is not rocket science here. We wash the dishes with hot water for a reason. Generally, the solubility of solid solutes in liquid solvents increase with increasing temperature. Like, here's your experiment for Saturday morning. Make pancakes and with syrup and wash one plate with the coldest water you have and see how long it takes for the syrup to come off. And we'll see you Monday. All right. And then one with the hot water and see. And you're like, okay, I'm not doing that. That's obvious. Hot water makes things dissolve better. Now, that is not 100%. We could have cesium sulfate and it decreases as you add temperature because it is an exothermic reaction and yada, yada. But in general, yep, that would work. Okay, so generally speaking, that's what happens. All right. The opposite is true for gases, though, which makes sense because earlier I said, hey, just remember they're the opposite of everything for solids, right? So the hotter, the less it will hold. That's why in the summer over at Pioneer Pond, fish die in August. The water got hot and lost its ability to hold the oxygen. And so they decrease, the oxygen decreases, the fish can't breathe and they're muerto. Now, pretty much your whole life, they've had a fountain, 2 of them, to help prevent that. When I first moved here, there was no fountain. And like literally like August 15th, a little timer went off and all the dead fish floated to the top because it just got to a certain temperature and then it was over. Okay, good. What? It does help decrease the moss as well. Okay, the rest of the hour, we're going to talk about chromatography, which isn't my specialty, but it's not hard. Who's had forensics? You did chromatography in there, right? Why have I given her my chromatography supplies for so long? Now I'm confused. All right. Chromatography is a process to separate a solution. Chromatography, there are 3 types. There's paper. And now get ready. There is thin paper and column. That's a weakness of mine. Is that spelled sort of right? Okay. You're confused on why there's these? Me too, bro. It's like, okay, whatever. We'll learn. We'll learn. They're 99% the same. Okay, we ready? This is actually kind of fascinating to our, like this very moment of our lives. Chromatography process is more applied than it ever has before. And you'll see why here in a second. All right. In chromatography, the components of a liquid solution. Sorry, I shouldn't have started that way. I'm just going to start how it's typed. The components of a liquid solution cannot be separated by filtration because if something's dissolved, they both go through the filter paper. You okay with that? All right. So whatever. It's too small. They go through. So we have to have some other way to do it. And we use chromatography. Paper, thin layer, sorry. Thin layer and thin paper, they're called the same thing very often. And column. They can be used to separate components of a solution due to attractive forces among the components of the mobile and stationary phase. And we'll talk about and define what these things are. But this is a pretty cool application of chromatography. This is called a COVID-19 rapid antigen test.
No,
Who's ever had one of those?
not the rabbit one.
Okay. So this is what they do. You swab your nose, right? And you kind of tap it, smear it onto that one little spot. You with me? Timmy's had one of these. He's got a false negative or false positive, I mean. I know you were. Okay, and they put that on there. That's where this part is. And then they put an analyte. That's the 6 drops. If anyone's ever done one of the maximal cells, you put some drops in this other area, and then you just close it and chill. And it takes about 15 minutes for the capillary flow. That's where the water flows up like the paper. If you've ever put a paper towel in water, you know water will climb up it due to this capillary flow. All right, and what happens is it takes the things from your nose, and if they bind with these 2 acceptors, then you get 2 lines. And if you get 2 lines, you're sort of screwed, right? It means you're positive. What's that? I don't know the chemistry behind that. That's actually biology. Well, the thing that would stop it is if it's not there.
Hey, so, okay,
So we good? So the yellows are there. Those are in our bodies. The red spikes are here. You'll only get a positive if you have the red spikes that bond with this test line. But you get this line here to prove that the process has actually worked. Does that make sense? Okay, I didn't think I understood your question at first, but okay. Now this is technically not chromatography. It's lateral flow immunoassay. That's hard to say, but it's the same exact idea. So this is a lateral flow immunoassay that qualitatively detects the presence of the N protein in nasal swab samples. You don't need any instruments. That's what's awesome about it. All the necessary reactions take place on the test card. 6 drops of test reagent are added to the top of the test card. Then the swab containing the patient sample is inserted into the second. Okay, this is like the lollipop version. Whatever. And rotated 3 times. The card is sealed. Within 15 minutes, the result will be displayed on a paper strip, similar to a pregnancy test that can be visualized through a small window on the front of the test card. Yeah. So I have never taken a pregnancy test. Never in my life. But I know, like, you pee on it. And then the chemicals in the female's urine will do this exact same thing. They'll carry up, and if you find the right things, a line will come, and that means, hey, I have something in my body that's growing out of control. All right. And in about 9 months, you'll eject it. And give me a better word. Give me a better word. It ejects. Your body literally says, this thing's too big. I got to get it out. I think I would know all about it. I've had 4 kids. Okay. All right. Anyway, I thought maybe you'd find that interesting, but maybe most of you didn't. Oh, okay. Thank you.
That's something I do find interesting.
this is related to biology.
It's not.
Okay, fine. Okay, fine. Okay, components of a liquid solution can be separated by processes that take advantage of differences in the intermolecular attractions of the components. So you can see why we teach this after we teach this. Chromatography takes advantage of the difference or of Wow, they don't usually screw up, but that's got to be of, right? Intermolecular interactions between and among the components of the solution. That's the mobile phase with the surface components of the stationary phase. Okay, it is important to find these two things right here, the mobile phase and the stationary phase. Okay, so the stationary phase, just an example, is the road that you drive on. It doesn't go anywhere, right? And in our example, this would be the paper. You sort of with me? Because you maybe did this in earlier grades. You take like a beaker and you have a tiny bit of water or whatever your mobile phase will be. You have this solvent here and you put a piece of paper in here that has like a red colored dot on it, like right here. All right. The mobile phase would be like the car that's going to drive on the road. It is the solvent that travels from the bottom of the stationary phase or paper up to the top. You okay with that? All right. And the thing you're analyzing is like the people inside the car. You with me? The car's going to take them. The car's going to travel because the road exists. And based on, this is the analogy kind of breaks down now, but based on the attraction between the things that the red dot is made out of and the paper, which we call the stationary phase, or the solvent, which we call the mobile phase, it will determine like how far up this paper it goes. And most of the time, as it travels up the paper, it leaves other things behind. Because red is a combination of colors. This will separate all of those colors into their separate components. Now, I have to make sure you know something. Chromatography is used to separate substances. Well, paper chromatography is used to separate them and see what's in there. But it is not something you can use to separate and collect substances. There's a chromatography that does that. That's column chromatography. But paper, we're just analyzing. We're not like separating and like getting it. We're just looking at, hey, that red dot was made out of these things. You're kind of all right with that? Okay, I'll come back, but let me show you this picture wherever it is. All right, will you hit the lights for me back there, somebody? It'll be easier to see. So I just did this yesterday, and all I did, you saw them sitting over there probably. I just took some M&Ms and got them a little bit wet, and then touched a piece of like the end of a stir rod to the end, and then dropped their color right here. So this was a red one. This was a yellow one. And any idea what this one was? It was green. Okay. And then I put this in my beaker, and I just had salt water. And then the water, which was polar. So the mobile phase was polar. The stationary phase here was nonpolar. Now, based on that information, we could come up with some information about the blue one. I'm just going to get rid of this whole thing. This blue section right here that came from the green, what would we say about it because it traveled so high up? It's more attracted to which phase? Mobile. It moved the farthest. Okay, it stayed in the car the longest. So it was attracted to the car more than it was the road. Are you okay with that? It was more attracted to the mobile phase, which we would say then really means blue is more what? What of these? Which one would it be? It's more polar. You okay with that? Okay, now size does matter on these, but really ultimately we're looking at its polarity, not the size of the molecule. If you look at them and they are the same type of molecule, then it would be the one that went the farthest was the smallest. But usually they're not the same type. Okay, we sort of all right with that? I'll come back and we'll talk here. All right. The solution or mobile phase will have a certain amount of intermolecular attractions to the surface components. Thank you, Preston. At my convenience. It's up to you. I'll let you choose. To the surface components of the paper or column due to differences in polarity. Okay, so they can be attracted to the paper. All right, but they'll also be attracted to the mobile phase. The more polar component of the solution, the less interaction it will have with the moderately polar stationary phase, and the farther it will travel. The less polar a component of the solution, the more interaction it will have with the moderately polar stationary phase, and the less it will travel, which is just what we said with the blue. If it made sense before, don't let these words confuse you. Blue went farther because it was polar, and so also was the mobile phase. So it moved with the mobile phase the farthest. Fair enough? All right, there's a lot of words, but I'm moving on. You all right with that? Yes. Oh, okay. So this is how you set up a chromatography setup. You would have just a beaker, your solvent, then whatever you're going to analyze, you'd put it on the paper. And then it's usually filter paper or chromatography paper. They work really well to do the same thing. Like the chromatography paper I have is the same exact as my filter paper. Okay, then you dip it in. It is extremely important that the ink spot does not go into the solvent. Okay, like if they ask you to draw one of these, and if you get a chromatography, you're going to have to draw it. You must do a good job to indicate liquid here, paper here, and your ink spot very clearly should be above the layer of the mobile phase, as they'll call it, which is just the solvent. Okay, as time goes on, you have your ink spot that travels up. And we now have separated into these 1, 2, 3, 4, 5 different layers. You okay with that? Now, I can't collect these, but I could use it to say there are 1, 2, 3, 4, 5. And I could use it more specifically if I really analyzed it to tell exactly what these were. There's ways to do that. All right. Individual pigments travel different distances up the filter paper because of the balance between their attraction to the mobile phase and their attraction to the stationary phase, which in English, I wish they would just say this, due to the balance of interactions between attractions between the solvent and their attraction to the paper. We okay so far? Usually we do this with water. It could be whatever I want. It could be hexane. It could be salt water. It could be anything really I want, but typically it's just water. All right. Now, you wouldn't use water if you were analyzing something here that was what? Like super nonpolar, because it wouldn't move at all, right? You would need some sort of interaction. So what you would do typically there is find a polar paper and a nonpolar liquid. Because you can switch them. It what?
You said it didn't matter what solution you put it in.
Well, it doesn't have to be an exact one, but like the solution should make, or sorry, the solvent should be something that would get the ink to move in the first place. All right. So here are some questions. This is not the full question. It's multiple choice, and I'll show you the next page here in a second. But in a paper chromatography experiment, a sample of a pigment is separated into two components, X and Y, as shown below. The surface of the paper is polar. All right, so this is polar. What can be concluded about X and Y based on the experimental results? If the water's polar, or the paper, if the paper's polar, then what do we know about hexane? Hello. You okay? I sure can. Yep, bye. Carly Benson to the main office, please. All right. So hexane must be most likely what? Nonpolar. What do we think it is? All right, there's no ions, there's no polar, there's no hydrogen bonding, it's just C's and H's, so it is. Okay, so Y goes here, X goes there. What can be concluded about X and Y based on the experimental results? All right, here are your options. I hope I don't have them circled. Okay, I don't. Okay, so this is the same question. It just is giving you A, B, C, and D to choose from.
This is a trick question. It's asking the question. So, okay, so hexane is not considered X would be more than okay. But then if there's a water, then it would be okay. Then it would then you would but so oh so like
All right.
I don't know if I was asking this.
So I heard great discussions behind me. Since hexane's nonpolar, the thing that travels with hexane the best would be also the one that goes with hexane would be nonpolar because likes take legs. Is that what you said?
Yes.
Okay, sorry, I just didn't hear you right then. I apologize. All right, but that's not an option. So it's analyzing which one went the shortest, which means that D, Y is more polar than X, because X went farther in the nonpolar car than Y could because it's not actually nonpolar. Are we okay with that? All right, I have 1 minute and 20 seconds left, which there's no way to do this in that amount of time. But you can read it and think, wow, I can't wait to start with this tomorrow. We better not test tomorrow. We'll finish and review. I'm like right there, but I'm not there. No test tomorrow.